Hi, students. In this note set, we're going to take a look at another way of representing the electron arrangement in an atom through a picture. And the picture is called an orbital diagram. There are lots of ways of representing electrons, and this one's a really interesting one. It's kind of fun, and it's not nearly, once you got the hang of electron configurations, I think orbital diagrams come pretty quickly. So very simply put, orbital diagrams are pictures of the arrangement of electrons within an atom. In the pictures, we're going to use arrows to represent the electrons. We're going to use boxes or sometimes blanks to represent individual orbitals. And we're going to group the boxes together to represent a sublevel. Here's an example. Take a look at the arrows, and you might say, geez, that doesn't look like an arrow. Sometimes scientists draw two sides of the arrowhead. Sometimes they just draw one. It's a little bit faster to draw it with just one side of the arrow. And so that's why this one is drawn that way. This element represented here has 2 electrons in the box labeled 1s. It has 2 electrons in the box labeled 2s. And it has a total of 1, 2, 3, 4, 5 electrons in the boxes that are together labeled 2p. Notice that there's a group of 3 boxes for the 2p sublevel because all p sublevels have 3 boxes in them, whereas s sublevels only have 1 box. This orbital diagram is for a neutral fluorine atom. Neutral fluorine has an electron configuration that ends with 2p5. In fact, I'm sure you could write the electron configuration: 1s2, 2s2, 2p5. Every single arrow is an electron, and every single box is an orbital. You might wonder, why are there 2 arrows in some boxes, but there's only 1 arrow here in this last box? We're going to address that shortly. First, let's recall a rule that we had learned when writing electron configurations. That was called the Pauli exclusion principle. What that said is, if an orbital has 2 electrons in it, they need to be spinning in opposite directions. Now, the real reason behind that has to do with the magnetic field that a spinning electron charge generates. And that's a taste of physics that we don't need to dwell on right here. For our purposes, what we need to know is, when we draw an orbital diagram, every arrow represents an electron, and if we've got to put 2 arrows in a box, one of the arrows should be pointing up, representing a spin in a clockwise direction, and the other arrow should be pointing downward, indicating a spin in a counterclockwise direction. So for our purposes in an orbital diagram, it's not okay to have 2 arrows in this 2s orbital pointing up. That is not a good orbital diagram. But below, you see every single blank, sometimes orbitals are represented with boxes, sometimes with blanks, but every single blank or box has 1 arrow pointing up and 1 arrow pointing down. That honors the Pauli exclusion principle. Okay, one natural question that people ask when writing orbital diagrams: does it matter whether I draw the up arrow first or the down arrow first? Nope, it absolutely does not matter. You could write the up arrow followed by the down arrow, or you could write the down arrow followed by the up arrow. That's totally fine. What you're not allowed to do, according to Pauli exclusion principle, is have 2 up arrows or 2 down arrows. There are a couple of other rules that we need to visit prior to digging into the orbital diagram concept. Okay, here's a nice familiar rule for us. The order of filling the sublevels in an orbital diagram is exactly the same as that for writing an electron configuration. I'm sure you remember 1s, followed by 2s, followed by 2p, then 3s, 3p, 4s, 4d, 3d, 5s, 4d, 5p, and so on and so forth. I encourage you not to memorize that. If you ever get stuck, all you need to do is list the sub-levels that do exist within every principal energy level and start drawing arrows. Swoop down from upper right to lower left, and you'll hit every sub-level in its order. In an orbital diagram, you'll see this same pattern shown. 1s, then 2s, 2p, then 3s, 3p, then 4s, 3d, 4p, 5s, and so on and so forth. Oh, and notice, this is kind of cool, all of the S sublevels, color-coded yellow in this diagram, have one box, because every S sublevel has one orbital in it. The P sublevels in this diagram, color-coded gray here, have each 3 boxes, because every P sublevel has 3 orbitals in it. The turquoise color represents the D sublevels, and every one of those lines has 5 boxes because there are 5 orbitals in every D sublevel. And then lastly, there's a couple of F sublevels, the 4F and the 5F. If you count up the boxes, and they're color-coded pinkish reddish here, there's 7 of them because there are 7 orbitals in an F sublevel. The idea that you fill the sublevels from lowest energy to highest energy is called the Aufbau principle. Electrons occupy orbitals with the lowest energies before moving on to other orbitals, and they always go in order. Basically, that's just restating the concept of ground state configuration. We never presume that an electron is excited. Indeed, that's a rare circumstance for an electron to have received energy in the form of a photon or other electromagnetic radiation wave and get promoted to a higher energy level. That's usually not the case. So when we draw orbital diagrams or electron configurations in this class, we're always going to draw them in ground state configuration. Another really important rule, it's called Hund's rule. Well, it's a German dude, so Hund is technically his name, but everybody says Hans. Hund's rule says that within a sublevel, every orbital receives 1 electron before any orbital receives a second electron. Check out the orbital diagram for oxygen here. 1s2, 2s2, 2p6. Yeah, it should say 2p4 here because there's 1, 2, 3, 4 arrows. 2p4. According to Hund's rule, if you've got to place 4 arrows in the 2p sublevel, then space them out if you can. So one of the 3 boxes needed to get a doubled up arrow because you couldn't fit 4 electrons in 3 boxes unless one of them was doubly occupied. But that leaves the other 2 boxes with 1 arrow each, rather than having a doubly filled orbital and an empty orbital. Here's another example. Phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. There are 1, 2, 3 arrows in the 3p sublevel, and each of the 3 boxes has 1 electron each, 1 arrow each. 1 electron per orbital, unless you have to double up, is a nice, succinct way to put it. Okay, let's take a little tour of orbital diagrams for the first just 10 elements. And I'm going to include the electron configurations along with them. So let's start with good old-fashioned hydrogen, which, if it's neutral, has just 1 electron. Its electron configuration, 1s1. Its orbital diagram just shows 1 box, labeled 1s, and there's only 1 arrow in it. It could be pointing up or down, it doesn't matter. Helium, atomic number 2, which means if it's neutral, there's 2 electrons. Electron configuration, 1s2. Orbital diagram shows 2 arrows in the 1s box. Lithium, atomic number 3. Electron configuration is 1s2, 2s1. Notice that the electron configuration exactly mirrors the orbital diagram. There is precisely the same number of arrows in the orbital diagram as is shown in subscripts or superscripts in the electron configuration. Beryllium, 1s2, 2s2. 2 arrows in the 1s box, 2 arrows in the 2s box. Boron, 1s2, 2s2, 2p1. Just add 1 arrow in the next higher sublevel, the 2p sublevel. Let's keep going here. We've added a new sublevel. Carbon, atomic number 6, 1s2, 2s2, 2p2. Notice all we're doing is adding 1 more arrow each time. Now, when we drew this arrow for carbon, the last one, notice that, according to Hund's rule, you would want to put 1 arrow per box in the 2p sublevel until you had to double up. So you would not show 2 arrows in the first box and then 2 empty boxes. Nitrogen, another arrow, ends with 2p3 for its electron configuration, and indeed there are 1, 2, 3 arrows in the 2p sublevel, 1 arrow per box. Oxygen, now we need to double up. 2p4 is its electron configuration ending. 1 of the 3 boxes in the 2p sublevel is doubly occupied, and the other 2 are singly occupied. Fluorine, now you've got 2 doubly occupied boxes in the 2p sublevel. And lastly, neon, well, that fills out the entire 2p sublevel. There's no other room for more electrons. Okay, one little twist. Sometimes when a problem about orbital diagrams is posed to students, it's going to ask you about the number of unpaired electrons. This is actually a pretty simple concept. The presence of unpaired electrons affects an element's magnetic properties, especially when it's found in metals. That's why they ask you that. And also, it's a nice question to ask as a follow-up to an orbital diagram. So here's an example of nitrogen's orbital diagram. And they're showing you that there's a pair of electrons in the 1s orbital, another paired up 2 electrons in the 2s orbital. And then we have 1, 2, 3 unpaired electrons in the 2p orbitals. So if they asked you how many unpaired electrons are in a neutral atom of nitrogen, you would have to draw out the orbital diagram, write out the orbital diagram, and then look for arrows that don't have a partner. In this case, you'd say there's 3 unpaired electrons. Let's revisit the orbital diagrams for the first 10 elements that we had just taken a look at, and let's ask ourselves, how many unpaired electrons are there in each one? Okay, so let's take a look at each of those 10 elements whose orbital diagrams we had seen earlier. Hydrogen has just 1 electron in the 1s orbital. That 1 electron does not have a partner. So yes, hydrogen has an unpaired electron, 1 of them. Helium, it has 2 electrons in the 1s sublevel, but they're paired up. There are no unpaired electrons in helium. Lithium has 1 electron in the 2s sublevel. Yes, it's unpaired. So there is 1 unpaired electron in lithium. Beryllium, everything's paired up. Each of the boxes have a doubly occupied arrow situation. No unpaired electrons in beryllium. Boron has one electron in the 2p sublevel. That one is unpaired, so one unpaired electron in boron. Let's keep going. Carbon. Carbon has 2 electrons. Remember Hund's rule. Hund's rule really matters here. In Hund's rule, you've got to put 1 arrow per box unless you have to double up in a sublevel. Well, because carbon follows Hund's rule, there's 1 electron per orbital, giving us 2 unpaired electrons in carbon. With nitrogen, there's even more. The 3 electrons in the 2p sublevel occupy 1 orbital each. That gives us 3 unpaired electrons. Oxygen, well, we've got 1 doubly occupied orbital in the 2p sublevel, but we still have 2 unpaired electrons. Fluorine, 1 unpaired electron. That last box has an electron that's alone. And then finally, neon, everything's occupied. Every single box has 2 arrows. There are 0 unpaired electrons in neon. Okay, let's put all of this together and try a couple of sample problems. How many unpaired electrons are found in a neutral sulfur atom? Now, the reason I'm asking you about unpaired electrons here is because it requires you to draw a good orbital diagram before you can answer the question of how many unpaired electrons there are. Let's start by looking on the periodic table. You've got to know how many electrons we're dealing with first. If you find sulfur on the P table, the whole number in the box is 16. That means that we have 16 protons. We'll always be assuming neutral atoms, and actually in the question here they say neutral, but you would otherwise still assume neutral atoms and ground state configurations. All right, we're going to make an orbital diagram. Since we know that the atomic number is 16, we're going to be drawing 16 arrows. We will draw arrows in boxes starting with the lowest energy sublevels first. That's the Aufbau principle. That means write your first 2 arrows in the 1s sublevel. Write the next 2 arrows in the 2s sublevel. Write the following 6 arrows in the 2p sublevel. Okay, and we're just going to work upwards from there. If you ever forget the order of filling sublevels, just make a sketch in the margins of your test or quiz, write out what sublevels exist, and draw those strike-through lines, diagonal strike-through lines, and that'll show you what sublevels are filled in what order. Okay, another couple of things to remember. Within a sublevel, draw 1 arrow per box unless you have to double up, unless there's no other place for the electron to go. That's Hund's rule. If there are 2 arrows in a box, make sure one of them is pointing up and the other is pointing down. That's the Pauli exclusion principle. And then lastly, to answer the question of how many unpaired electrons there are, we're looking for arrows that don't have a partner. Okay, so here we go. 16 arrows written in the sublevels from lowest energy to highest energy. So 1s, then 2s, 2p, then 3s, then 3p. If you counted up all of these arrows, it'll add up to 16. So we've written the orbital diagram. Now we're just going to look for electrons that don't have a partner. How many arrows are alone? It's these last 2. 2 unpaired electrons in a neutral atom of sulfur. How about this? How many unpaired electrons are found in a neutral aluminum atom? We're going to follow the exact same strategy, but aluminum has a different atomic number. Aluminum's atomic number is 13, not 16. We'll make an orbital diagram, drawing 13 arrows for the 13 electrons. We'll start with the lowest sublevel first. That's the off-bow principle. Within a sublevel, draw 1 arrow per box, unless you have to double up, Hund's rule. If there are 2 arrows in a box, make sure one of them is pointing up and the other is pointing down. That's the Pauli exclusion principle. And then lastly, to answer the question of how many unpaired electrons there are, we're looking for arrows that don't have a partner, arrows that are alone. So once again, we're going to draw an orbital diagram first. You can draw orbital diagrams with blanks and then arrows above the blanks, or you can draw boxes. Either way is fine. In this case, let's draw a box for 1s1. We'll draw a box for, the 1s sublevel. We'll draw a box for the 2s sublevel. We'll draw 3 boxes for the 2p sublevel, 1 box for the 3s, 3 boxes for the 3p sublevel. And as you're good at electron configurations at this point, we know that the electron configuration ends with 3p1. That means there's 1 arrow in the 3p sublevel. And that 1 arrow that's alone is the unpaired electron. So for neutral aluminum, there is 1 unpaired electron.